Logic gates, such as this NAND gate shown here, have both a contamination delay and a propagation delay. We can also look at the contamination and propagation delay of a logic circuit such as the one shown here. And these delays relate to when the inputs change to when the output here changes. First then, we need to define what it means for an input to change and what it means for an output to change. Here I have an inverter and I can apply an input voltage to it that varies in time, and then I can look at its output voltage, which again will vary with time. Of course, in a realistic circuit, the output of this gate will drive other gates. They will add a capacitance here, and that will affect what the output waveform will look like. But I will just draw some figures here so we can understand what we mean by inputs changing and outputs changing. Let's assume at time t less than 0, the input signal here is at 0, and then due to the circuitry driving this logic gate, the input is going to rise up. Maybe there are some glitches or whatever, it comes back down, rises up, maybe a little oscillation here, and then it might stay at a logic 1 level here. This represents an actual voltage waveform, such as what you might see if you use an LT spice simulation of how the FETs in a logic gate work. To make digital system design tractable for humans, we want some relatively simple models. In this particular case, we just want to know two things about this input signal. The first thing we want to know is when did it start to change? The second thing we want to know is when did it arrive at its final value? You might be tempted to say it started changing at time t equals to 0, but that's forgetting that real signals are likely to have noise on them and are constantly going to be changing. So we can't say it's changed at precisely t equals to 0. Instead, we need some other method of deciding when a signal at the input to a gate has changed. Indeed, this is the very reason we have two concepts, V input high and V input low. Let's remember what these two constants tell us about our logic gate. By the way, on a manufacturer's data sheet, you will find these values here. So these are values given to us by the maker of the logic gate. Let's call the input to our logic gate V in. If V in is less than V input low, then this logic gate recognizes that its input is at a logic 0. If V in is greater than V input high, then this logic gate recognizes that its input is at a logic 1. Therefore, the question of when the input first changes becomes a question of when the input first either exceeds V input low if it was originally 0, or when it first is less than V input high if it was originally a 1. You can think of V input low, V input high as giving us a region. If we start at 0 volts, then we're certainly below V input low. As we rise up, there comes a point when we're at V input low. Above that, we're at an undefined voltage. Then at a higher level, there's going to be V input high, and above that, we're at a logic 1. So we have got 3 regions. If we assume in our diagram that this is V input low, and this is V input high, these are the two thresholds here, then our signal first changes when it crosses V input low for the first time. When it's between V input low and V input high, then it is undefined. It is neither a logic 0 nor is it a logic 1. When it pops up here, it is a logic 1, but this lasts only temporarily. Due to glitches, it then falls down into this undefined region. It then goes back to 0, then it's undefined again, then it's a logic 1, then it's undefined again, and then it's a logic 1, and it stays a logic 1. So in terms of when does it reach its final value, not here because it's still changing, and not here because it's still changing, but right here is when it reaches its final value. This is the last time it exceeds the V input high level and stays above there. So we can answer our question. It first changes right at this point here, and it reaches its final value right at this point here. And it's the times we care about, at this time and at this time. In between here, it's transitioning. Before here, it has not changed. And after here, it has reached its final value. When we measure contamination delay, we take it from when the signal first changed. And when we measure propagation delay, we take it from when the signal finally becomes valid. We now need to look at the output of this logic gate. Don't look too closely, it's not very realistic compared with this input, but let's pretend that the output of this logic gate looks like this. Once again, we need to answer two questions. When did the output first start to change, and when did the output reach its final value? Now we answer these questions in almost the same way we answered it on the input side. The only difference is we have two different thresholds. And I'll explain why we have two different thresholds after I've told you what they are. For the output, we have V output high and V output low. If I call the output here V out, then if V out is greater than V output high, then the output is valid and it's a logic 1. If V out is less than V output low, then the output is deemed as being valid and representing a logic 0. Once again, V output high and V output low are given to us by the chip manufacturer. Roughly speaking, as in if we ignore dynamic effects, if the input is valid, meaning that the input is either greater than V input high or the input is less than V input low, if the input is valid, then the output is going to be valid according to this criteria here. That is, it's either going to be above V output high if it represents a 1, or it's going to be less than V output low if it represents a 0. Imagine for a moment that this logic gate is connected to another logic gate. If its output is valid, let's assume it's a valid 1. So if its output is valid, it means its output is above V input high. We would very much like that the next gate recognizes that its input is a 1. This means that if this gate is outputting a value, then it must be greater than V input high for the next gate to be able to understand it as a logic 1. If the criteria here that the output of this gate is a logic 1 is that it's above, say, 4 volts, then it's essential that the input to this gate recognizes any number above 4 volts as being valid. So this input high here has to be no greater than this V output high here. This has to be more tolerant than this. This needs to be closer to the supply rail. This needs to be more tolerant. Now, since we want to allow for the fact that noise might be present or other factors, we actually want to have a noise margin. We want this guy here to be less than this guy, and the greater the difference, the better the noise margin. Put simply, a nice logic gate is one that is sloppy on its input. It allows for noise, but is very tight on its output. It's very precise on its output. The same concept occurs for the input and the output being a logic 0. We want that the V input low is relatively relaxed, so V input low is going to be larger than V output low, which is going to be strict or quite tight, and the greater the gap, the better the noise margin is going to be. On the output side, I've now drawn the levels for V output low and V output high for this logic gate here. Remember, whenever the output is above V output high, then the output is taken to be a logic 1. if the output is lower than V output low, then its output is taken to be a logic 0. This is based on the output criteria, which is tighter than the input criteria here. You'll notice I have tried to draw V output low at a lower level than V input low, and V output high at a higher level than V input high, for the reason I said before, we want to have robustness to noise. To answer when our output first changed, then we have a look here. We see that the output, which before time t equals to 0, has just remained at a logic 1. After time 0, it's still recognized as a logic 1. It's when it first crosses the V output high, that's the first time that the output becomes invalid. So when the output is between these two limits, it's deemed as being invalid. And when it's above V output high or less than V output low, then the output is deemed as being valid. The same as for the input. The input is invalid in this region here and valid outside that region. Coming back to the output, the first time the output became invalid is here, and it reaches its final value the very last time it becomes valid, which is over here. Marking these in red, we see that this is the time when the output first became invalid, and this is the time when the output finally became valid. And the contamination delay is the time from when the input first started to change to when the output first started to change. If, for example, the input first started to change at 1 nanosecond, and over here at t equals to 2 nanosecond, the output first started to change, then in this particular example, the contamination delay would be 1 nanosecond, the time from when the input first changed to when the output first changed. Similarly, the propagation delay is the time from when the input finally becomes valid to when the output finally becomes valid. If this occurs at t equals to 6 nanoseconds, and this occurs at t equals to 10 nanoseconds, then in this example we'd have a 4 nanosecond propagation delay. In terms of basic concepts, that's all there is to it, so let's summarize. Given a logic gate, we look at its input and its output. Now, technically, we need to do this over all possible types of input transitions. Here I just have a single input logic gate, but I might have a 2-input logic gate, and the way that the inputs change will affect what the output looks like. And if I have a whole logic circuit, like when we started, I had 4 inputs and 1 output, then I have lots of different ways that the inputs can change, different waveforms, etc. And I essentially have to look at the worst case behavior. I have to look at the worst contamination delay and the worst propagation delay. But for this exercise here, let's just look at a specific example. We assume that the input looks like this and the output looks like this. For this particular example, if we're asked to find the contamination delay, then we need to look at when the input first changed, we need to find when the output first changed, and the time it took between when the input first changed and when the output first changed is the contamination delay. Similarly, the propagation delay, we first find when the input was finally valid, we then find when the output is finally valid, and the difference in time between when the input was finally valid and the output was finally valid is the propagation delay. So we now just need to know what it means for the input to first change, the output to first change, the input to be finally valid, and the output to be finally valid. And this is given by our different voltage thresholds here. We've got 2 different thresholds, but the same concept. We've got the input thresholds, which are a bit looser, a bit more relaxed, and we have the output thresholds, which are a bit tighter, a bit stricter. The input changes when it first becomes invalid. Invalid means it lies within this region here, between V input low and V input high. Below V input low, the input is recognized as being logic 0. Above V input high, the input is recognized as being a logic 1. In between here, it's invalid. The first time the input becomes invalid is when we say that it has started to change, and that's when we start our timer. We stop our timer when we're timing the contamination delay when the output first changes. Similarly, the output first changes when it first becomes invalid at this red line here. So that's the contamination delay, time from when the input first changes to when the output first changes. For the propagation delay, we need to know when the input is finally valid. To do that, we essentially go backwards. We find when the input is valid and stays valid, and we go back to when it first becomes invalid. And so this is the last time when it's finished being invalid and becomes correct, the true final value here. We start our timer at this point. We stop our timer when the output is finally valid for the last time. And the time between here and here is the propagation delay. That concludes the basic theory, but let me make several comments. The first, as I mentioned before, is that here we studied a specific example, but depending on how the input changes, depending on the temperature, depending on if we had multiple inputs, the order in which they changed and how they changed and whether glitches were present, etc., each case will cause the output to be different. And so the true contamination delay of a logic gate has to be the worst case behavior. And similarly for the propagation delay, the true propagation delay has to be the worst case behavior. And there should be some margin for error as well. The second comment to make is that what I have presented is a very academic definition of propagation and contamination delays. It's very nice because it's very rigorous and precise, but because in real life it's hard to measure these delays here, or more accurately I should say it's very hard to go through every single possible input to find out every single possible output and analyze this in each case. Often manufacturers measure propagation and contamination delays using somewhat less academic means of measurement, and so therefore you're going to find some discrepancies in the literature. Nevertheless, the basic concept is precisely as presented. The benefit of a contamination delay is that if we have got a flip-flop at the other end of a logic gate, then the contamination delay gives the flip-flop a chance to photograph the old output before the new output comes along. The propagation delay we normally want as short as possible, but it physically exists and therefore we have to take it into consideration, such as when we are computing Fmax for a sequential logic circuit. The only other comment I want to make is in the case of when we are dealing with ideal input-output signals for convenience. If the input is this ideal signal on the left here, then the input first changes at the rising edge, and it is also valid at the rising edge. So therefore these two red lines up here have become a single red line under this ideal model here. Similarly for the output, I've shown an output without any glitches, so therefore at this point here, this takes the place of both these red lines here. In this case, both the contamination delay and the propagation delay are equal, and it's the time from when the input has first changed to when the output has first changed, because first changed and final change are the same thing, so both the contamination delay and the propagation delay are just the time between these two events here. If instead my output does have a glitch, then even though at the input there's just a single red line, at the output side we now are back to having our two red lines. The first red line is when the output first changed, and the second red line is when the output finally took on its correct value. In this case, the contamination delay is the time between the first two red lines, and the propagation delay is the time between the first red line over here, which is also the second red line, so to speak, it's two lines on top of each other, and the second line over here. Come to think of it, there's one final note to make, and that is that the output behavior here depends on the logic gates that this logic gate is driving. Due to fan out, if this logic gate has to drive more than one logic gate, then it's going to be slower to respond, and so you'd expect that at least the propagation delay is going to be longer. When chip manufacturers state the contamination and propagation delays, they state under which conditions they are valid, and for example, they will include the largest capacitance at the output that this logic gate is allowed to drive, under which these delays are going to be valid. Remember, the greater the fan out, the larger the capacitance is going to be that this poor logic gate has to drive, and the slower it can respond.